Hello. Hello.
Yes, sir.
Yeah. You have a query?
No, sir. We can hear.
Okay. So let's start. Now, in this format, we need to revisit some of the things that we have already talked about, because everything cannot be emphasized at one shot. Okay. So let us look again at the global balance of total energy. This is the first law of thermodynamics. Now I'm writing it for an open system or a control volume, which has one inlet and one outlet. So the assumption is the flow is steady and the variation of the flow quantities across the inlet and outlet are uniform. So we can say it's a kind of one-dimensional flow at the inlet and a one-dimensional flow at the outlet. Now, we need to be careful about the sign convention in these terms. Now, we have one term m dot, which is the mass flow rate in kg per second. We have a term q dot in, whose units is watts, and we have another term which is w dot shaft, which is in watts. Now here, the way it has been written, the subscript 1 refers to the inlet and the subscript 2 refers to the outlet. Okay. And it is tacitly assumed that m dot is a positive quantity. So in this equation, you have to keep in mind the fact that the m dot is the magnitude of the mass flow rate. And if you're using SI units, the units will be kgs per second. Now suppose m dot were negative, then the inlet and outlet would get interchanged. Okay. So that is you have to understand the sign convention, otherwise you will end up getting numbers which do not reflect reality. So m dot is always positive as far as this equation is concerned, and this is something which will not be stated in this manner in any book on thermodynamics. Pardon? I couldn't get you. This mass flow rate, we are assuming it is positive. It's a positive number. If the mass flow rate were negative, then the 2 will become the inlet and 1 will become the outlet. Okay. So the convention that we are using while writing this equation is the section 1, the subscript 1 refer to section 1, that is the inlet. So this is the energy which is flowing in. This is the energy flowing into the control volume which is convected by the mass. Okay. And the second term here, q dot in, is the energy flowing into the system from outside as heat. Okay. And on the right hand side here, this term represents the energy that is flowing out of the system through the outlet, which is section 2. And this is convected by the mass. And this W dot is the energy as work that you're getting out of the system. So W dot can be plus or minus, can be either positive or negative. Similarly, Q dot in can be positive or negative. But the way we are writing it, if I say 1 is the inlet and 2 is the outlet, then m dot has to be a positive number. Although it may not be stated in this form in any book, but it is understood that you know what it means. Now here I have put the subscript in, means this is the heat that is coming into the system. So in all textbooks on thermodynamics, the sign convention that is used for heat is that if the energy in the form of heat enters the system, it is considered to be positive. And if energy in the form of heat leaves the system, then it is considered to be negative. So Q dot in, if it's positive, that means some heat has entered the system. And if Q dot N is negative, that means some heat has left the system through the boundaries of the control volume. Similarly, W dot shaft is positive if you are extracting work from the fluid, and W dot shaft is negative if you are doing work on the fluid. Now in this course, we will be dealing with hydraulic turbines and centrifugal pumps. In the case of a turbine, this W dot shaft will be a positive number. So work is done by the system. And in the case of the centrifugal pump, you will do work on the system. So W dot shaft in that case will be negative. So we'll be interested in that case, in the case of the pump, in the magnitude of the shaft work. But the algebraic sign for the pump will be negative. W dot shaft will be negative for the pump and positive for the turbine. Similarly, Q dot in will be positive if energy enters the system as heat, or negative if energy leaves the heat. Now, this same equation may be used by Professor P.K. Das in power plant engineering. And if he applies it to a boiler, he will have W dot shaft 0. And he'll be dealing mainly with the heat. Now, I'm talking about the turbine, so I'm not interested in the W dot heat, Q dot in. So we are not deliberately adding any heat or taking out heat. We are going to either extract work or do work. So we are interested in W dot shaft. However, even if you are not adding deliberately any heat or taking out heat, if the fluid inside the system is at a higher temperature than the surrounding, there will be some inevitable heat transfer. It may be a small quantity, but it may be there. So if the temperature of the fluid inside the control volume is larger than or higher than the temperature outside, this Q dot N may be negative. All right. So now I have explained the physical meaning of these terms. H is the enthalpy. V, capital V, is the magnitude of the velocity. So half V square is the kinetic energy. So this is kinetic energy per unit mass. And G dot R minus G dot R is the potential energy per unit mass. So the fluid which is entering the control volume has some kinetic energy, some potential energy, and enthalpy. So this left hand side, the first term is the energy that is flowing into the control volume through the inlet. It is convected in by mass. And this Q dot in is the energy in the form of heat entering the control volume. On the right hand side, this is the energy which is flowing out. Again, it is convected by mass. And this is the work that you extract. Now, since we are interested in W dot shaft, what we did last time in the morning session, we divided the whole equation by m dot first and wrote it in this form, and then we kept this work term on the left hand side of the equation and moved all the other terms to the right hand side. So we can see how this work, from where the work is coming. Okay. So you have a group of terms in parentheses here, 3 terms and another 3 terms. So these are the quantities at the inlet, and these are the same quantities but at the outlet. Now, here I have grouped the terms in a different way. So I've looked at the difference of the enthalpies, the difference of the kinetic energies, and the difference of the potential energies, and the heat which is added. So the work that you're getting, the shaft work per kg per second, per unit mass per day, W dot shaft by M dot, is equal to the decrease in the enthalpy of the fluid plus the decrease in the kinetic energy of the fluid plus the decrease in the potential energy of the fluid plus the heat that is added in. Okay. Now, the enthalpy itself I can write as, this is specific enthalpy, that is units, SI unit will be joule per kg. Since it's very large, it could be expressed in kilojoule per kg. But when you substitute into the equation, to get the units right, you have to convert the kilojoule to joule per kg. So we can write the specific enthalpy as the sum of the specific internal energy plus this is the flow work, pressure times the specific volume. And specific volume, the units are meter cube per kg. we can write it as 1 upon rho, the reciprocal of the density. So we can write it as E plus P by rho. Now in this course, we are dealing with the flow of water, which is a liquid. So rho can be taken to be a constant. So the change in enthalpy, so change in specific enthalpy is related to the change in the specific internal energy plus 1 upon rho times the change in the pressure. So if using this fact, if I go down now here, so this equation now I've rewritten by using the relation H equal to E plus P by rho. So first I have just substituted blindly what is H. It is H1 is E1 plus P1 by rho. Now I have not used any substitute on rho because rho 1 equal to rho 2. So I am simply calling it rho. And this H2 I can write as E2 plus P2 by the same rho. Having done that, it's convenient to group it in a different way. The work done, rate at which work is done by the shaft, W dot divided by the mass flow rate, I can write as the decrease in the specific internal energy plus 1 upon rho times the decrease in the pressure plus the decrease in the kinetic energy of the fluid plus the decrease in the potential energy, gravitational potential energy of the fluid plus the work heat term. So for the sake of completeness here, I have written down what is P1 and P2. They are the fluid pressures at sections 1 and 2, which we assume is the same over the entire cross section at the inlet and entire cross section at the outlet. Similarly, E1 and E2, small e1, so lowercase letters indicate specific properties. These are the specific internal energies of the fluid. So units will be kilojoule per kg. But when you do calculations, you have to convert it to joule per kg. All right. Now what I will do is this term, which is the abstract term, I'm going to push to the right hand side, and these are measurable quantities which represent the change in the mechanical energy. So I'll write it as regroup it in this form. I'm grouping the change in internal energy plus the heat term together in parentheses over here, and I'll explain in a minute why I have done it this way. Okay. So the first term reflects change in pressure. Of course, it's not just the change in pressure, it's the change in pressure divided by the density. Okay. The second term is the change in kinetic energy, but to be more precise, it is a change in kinetic energy per unit mass. Okay. But whatever it is, it's proportional to the change in kinetic energy, and the first term is proportional to the change in pressure. And the third term here is proportional to the change in the potential energy. It is gravitational potential energy. But I have not written everything here because it will become very cumbersome. So when I talk about potential energy, you must understand it is the gravitational potential energy. So the sum of these first three terms represent the decrease in the mechanical energy of the fluid. And then you have the decrease in the internal energy and the heat which is added. Okay. Now, having done that, I'll talk about head loss. So I'll stop sharing this document and go back to the document which I was using in the morning. Okay, now in the morning session, we had talked about head and head loss. So I'll quickly refresh your memory. We were talking about head loss along a streamline in duct flow. So we're considering 2 points which we are labeling 1 and 2 on a streamline. And 1 is the upstream side of the streamline and 2 is a downstream point. That means the fluid particle is moving from point 1 to point 2. If I say H subscript 1 is the head, that is the sum of pressure, kinetic energy and potential energy in units of meters at point 1. And if H2 is the corresponding head at 2, usually H1 will be larger than H2. So So this difference H1 minus H2 is called the loss of head. This loss of head will be zero if the fluid is an inviscid fluid. But if it's a viscous fluid, the energy will decrease, the available energy. So the head loss for a constant density fluid, or to be more precise, head loss between sections 1 and 2, is the difference of the pressure, kinetic energy and potential energy at 1 minus the same quantities at 2. Okay, so it's convenient to write it in the form of which I've shown in equation 9. I've factored out 1 upon g here. The division by g is done so that each term has units of meters. And within the square brackets, I've shown the contribution to the head loss from the change in pressure. That's the first term. And the second term is the contribution to the head loss from the change in the kinetic energy. And the third term is the contribution to the head loss from the change in potential energy. Now, I've just shown the first law of thermodynamics in the other document. I've written it over here. Okay. So here I have written it in a form which is useful for this course. I have the work term on the left hand side and the terms which contribute to the work on the right hand side. So first term was the contribution from change in pressure. Okay. So compare this term with this term here. You see that within the first term in the square bracket here is the same as the first term in this equation. Similarly, the second term, the change in kinetic energy is over here, and the third term is the change in potential energy. And when you are applying the first law of thermodynamics, you are looking at total energy. So you have to consider the internal energy also. The internal energy is due to the microscopic motion of the molecules. So here you have a term involving the change in the specific internal energy and some heat transfer. Now, for viscous flow through the duct, there is no shaft work. So W dot shaft is 0. So the left hand side of this equation is 0. So if I move this term over here within parentheses, whatever you have on the other side of the equation, okay, you see that P1 minus P2 upon rho plus half V1 square minus V2 square minus this G dot R1 minus G dot R2 is equal to E2 minus V1 minus Q dot by M dot. So this equation I have labeled equation number 10. Now look at the term on the left hand side of this equation, and you go back and look at equation 9. You see that apart from the G factor, what you have on within the brackets, square brackets here, on the right hand side of equation 9 is the same as what you have on the left hand side of equation 10. All right. So if I go to equation 9 and multiply both sides by G, then the right hand side will be the head loss. GH, G times head loss, and that is what you have over here. Okay. So this left hand side then I can write as G times head loss between sections 1 and 2. So I have introduced the definition of the head loss and looked at the global balance of total energy and found this relation that G times the head loss is E2 minus E1, the change in the specific internal energy, minus Q dot by M dot. So I can identify head loss as 1 upon G times this quantity. The division by G will get each term on the right hand side in units of meters. And again, I want to emphasize 1 is the upstream side and 2 is the downstream side. So the fluid particles will be moving from 1 towards 2. So there is a direction involved. So on the right hand side, the first term here is the increase in the specific internal energy as the particle moves from 1 to 2. So the specific internal energy of the particle at section 1 is E1, and when it moves to section 2, the value has changed to E2. The change is because of the energy transfer. And you have this term minus Q dot by M dot. So suppose the fluid inside the control volume is at a higher temperature compared to the surroundings, then heat might flow from the fluid through the walls, solid walls of the control volume to the surrounding. In that case, Q dot in might be negative and you already have a minus sign. So this part contains, so the head loss term has a term involving the increase in internal energy and heat transfer to the surroundings. So we can give a physical interpretation. Head loss results in an increase in the internal energy of the fluid and possible transfer of heat to the surroundings. So Q dot N, if it is 0, then there is no heat transfer to the surroundings. But usually Q dot N might be negatives. So in that case, heat will be transferred from the fluid to the surroundings. Of course, you could have cases where it is the opposite. But usually it's this way. Now, you know that energy can neither be created nor destroyed. So when you talk about loss of head, you're talking about loss of available energy. But that means that mechanical energy that is being lost must be going somewhere else. So what is happening? So this analysis has told you what is happening. The decrease in the mechanical energy is represented as an increase in the internal energy and heat transfer to the surroundings. Now, this results in a loss of available energy because it's not easy to convert internal energy of a fluid to work. It's easy to convert the pressure, energy held by pressure to work. It's easy to convert potential energy of the fluid to work. It's easy to convert the kinetic energy of the fluid to work. And the conversion of the mechanical energy to work does not have any restrictions imposed on it by the second law of thermodynamics. Okay. So the efficiencies can be very high, even close to 100%. It will not be 100% because there will be some viscous losses. It is reflected by this term. Okay. But the internal energy increase is not a good thing for an engineer. So this term E1 minus E1 represents the increase in specific internal energy as the fluid moves from the upstream section 1 to the downstream section. And the term minus Q dot in by m dot represents transfer of heat in energy in the form of heat to the surroundings due to the rise in temperature caused by increase in internal energy. Now Q dot n, the minus sign, minus Q dot n is the energy flowing out of the control volume according to the sign convention. Because if Q dot n is positive and there is a minus sign, then the energy will be coming in. So if Q dot n is negative, minus Q dot in means the Q dot out. Okay. So according to the sign convention, Q dot out is minus Q dot in. So because of the minus sign, this represents the energy transfer from the system to the surroundings. Okay. Now some of you will take a course on convective heat transfer next semester. It is a core course for the 4th year dual degree students of thermal science and engineering. It's also an elective for BTech students. Okay. So there you will study this in more detail and you will come across a term called viscous dissipation. Okay. So in this course, I'll just simply say this, that it is what you may call fluid friction, but it is internal fluid friction. So if you consider what is happening at a point which is adjacent to a solid surface which is stationary, the fluid may be flowing past it, but if it's a viscous fluid and it satisfies the continuum hypothesis, then the fluid will stick to the solid surface. So the velocity of the fluid particle sitting on the surface is 0. So although there is a viscous force on that particle, no work is done against that viscous force. All right. So in a three-dimensional viscous fluid flow, when you have fluid flowing past a solid wall, although you have fluid friction at the solid surface, the interface between the solid and the fluid, because there is no displacement, the particles are stationary, there is no work done. However, because of the no-slip boundary condition, there will be a velocity gradient inside the fluid. Now, different layers of fluid, when they flow, they'll glide against each other, and there will be friction between different layers of fluid. And there will be some work done against the viscous forces between adjacent layers of fluid, which is inside the control volume. So it is internal fluid friction, and that is, to be more precise, I have not written it here, is called viscous dissipation. And it is an irreversible work. That is, you are always going to convert mechanical energy to internal energy. You cannot do the reverse. You cannot convert internal energy to mechanical energy. That will lead to a violation of the second law of thermodynamics. So this head loss is actually associated with an increase in the entropy of the universe, which you may call generation of entropy or production of entropy. And this generation production of entropy, you know, must be positive. Or if it's an ideal case, it is 0. So if the fluid is an ideal fluid, then this head loss term will be 0. All right. Now, yeah.
Sir, can you go back to the formula for head loss 1 upon G E minus E2 minus E1?
This one.
Yes,
Equation
sir.
11.
Yes, sir. Sir,
Okay.
why is this gravitational acceleration playing this much role? Meaning, if we did the same experiment or run the same turbine in moon, then head loss would be different. How is it so?
No, I didn't get you. Sorry.
Sir
How did I
means
get this term?
no, sir. Why is this gravitational acceleration playing this important role?
No.
Means
This is just is not playing a role. This is just okay. You tell me what are the units of head loss?
energy.
No, SI unit of head loss.
Meter.
Meters. Okay, but if you look at the specific internal energy, what is it? It is joule per kg, right? Now,
Yes,
joule
sir.
is Newton meter. Now, Newton is kg meter per second square. All right. So, what if you convert it? Then it will be what? The kg will cancel out, and you will get meter square per second square. Okay. So this 1 upon g is meter per second square. So if you divide meter square per second square divided by meter per second square, then you'll get meters. So this g is just introduced by hydraulic engineers so that E2 minus E1 by g has units of meters, and Q dot in by m dot g will have units of meters. That's all. Okay, so when you're writing the mechanical energy equation, see, when I wrote the first law of thermodynamics, if I go back over here, there was no G. Okay. Sorry, it's not in this. Okay. But when you are defining the head, okay, you're defining the boundary function by rho G. Why are we doing it? Just so that each term is in units of meters. So traditionally, hydraulic engineers, they like to deal with units of meters. That's all. All right. Now, I've already answered this question. Consider steady viscous flow of a constant density fluid inside a duct. What is the work done against the viscous force at the duct wall? The answer is that this is 0 because the velocity of the fluid particle is 0. Of course, assuming that the fluid is a continuum fluid. All right. Now, let me ask you another question. If you look at steady flow, the streamlines are fixed in space. What is the head loss between 2 points on a streamline in steady flow of a constant density in viscid fluid in a gravitational force field where the gravitational acceleration is a constant vector? So all these three, yeah, what's the answer?
0.
0. Okay, so the head loss is because of viscous effects. So when you're dealing with an ideal flow, there's no loss of head. Okay, now having introduced this head loss term, what we'll do is we'll write the energy equation using the head loss term. So as you can see, the internal energy is an abstract quantity, and hydraulic engineers don't want to deal with internal energy. So if you come back to equation 10, this is of course for the case where there's no shaft work, but I can go back over here and look at this equation, which is the case where you have heat transfer, work transfer, everything. Okay, but this whole quantity, suppose that the heat transfer is solely due to the temperature difference. You're not intentionally adding any heat or taking out any heat. Then this term, in parentheses, the last group of terms, that can be identified as the head loss term. Okay, so we can write the first law of thermodynamics using a head loss term.
So just a clarification is needed.
Yeah.
You told, can you just show that second question which you just asked?
Okay, sure. Yeah.
So
Yeah.
in that question, you said head loss would be 0.
Yeah.
So when there is inviscid fluid, then there is no work done against the viscous forces, and the internal energy won't increase at the end of the duct. And we say head loss is 0. But what about the heat lost? We don't know anything about that.
Okay. So let me talk about ideal fluid flow, something which you have studied in your second year. You tell me what is an ideal fluid. So in the morning, I said it has constant density and zero viscosity. But to be more precise, it also has zero thermal conductivity.
Okay.
Think about it. The transport process which leads to viscosity and the transport process which leads to conduction of heat, okay, they are identical. They are due to molecular diffusion. Okay, so if you say the fluid is an ideal fluid, the thermal conductivity is 0, so the heat transfer will be 0. Okay, and if you say viscosity is 0, the viscous force is 0. Of course, this is an idealization. There is no fluid which will be an ideal fluid, but it does not lead to a violation of the second law. Okay. Now let me ask you another question. Can you have a fluid with negative viscosity?
No, sir.
Can you have a fluid with negative thermal conductivity?
No, sir.
What will happen if you have a fluid with negative thermal conductivity or negative viscosity? There will be a violation of the second law of thermodynamics. Okay. There will be a violation of the second law. So if you take the course on convective heat transfer, this will be covered in detail over there. Here I'm just mentioning the results. But if you have zero viscosity and zero thermal conductivity, there is no violation of the second law of thermodynamics. However, if you have zero viscosity and zero thermal conductivity, the generation of entropy is 0. That means all processes, thermodynamic processes, will be reversible processes. So I've written those points over here. This I've already mentioned. The head loss in the flow of an ideal fluid is 0. There is no head loss. And the rate of entropy generation or entropy production due to irreversibility is also 0. And all processes involving an ideal fluid are reversible processes. So does that answer your question?
Yes, sir.
Okay. So you will not have head gain. That's what I mean. Okay. The head gain might violate the second law of thermodynamics. So you can convert mechanical energy to internal energy, but you cannot convert internal energy to mechanical energy. And that is why getting work by decreasing internal energy of a fluid is not easy. You will not, even if you try to do it, you cannot have a process which will have 100% thermodynamic efficiency. All right. Now let us talk about something which is called the modified Bernoulli equation. So what we'll do is we have looked at the relation between the head loss and the change in internal energy and heat. Okay. Of course, this is for the case when you are not intentionally adding or taking out any heat. So this heat transfer is unavoidable heat transfer because of temperature differences. Okay. So if I take this equation 11 and substitute into equation number 10, okay, the right hand side of equation 10 is similar to the right hand side of equation 11. The difference is this term 1 upon g, and as I've explained, the g term is there only to convert the units. You want the units of each term in this equation to be in units of meters. So therefore, the right hand side of equation 10 is g multiplied by the head loss. Okay. So I can write the equation in a form where it does not have the change in internal energy and heat.
Hello.
So you will come across this equation.
Hello, sir.
So this equation 12a actually is the definition of the head loss. Okay. The head loss is the loss of head, that is the difference of head. So the head at the upstream section 1 is equal to the head at the upstream section 2 plus the loss term. The loss term is positive, so that means the head at the upstream section will be larger than the head at the downstream section. And had it been an inviscid fluid, the head loss term will be 0 and the two heads will be equal. Okay. So this you can call the engineering Bernoulli equation or a modified Bernoulli equation, where you are accounting for the loss of head, which you cannot do if you assume the fluid to be an inviscid fluid. Okay. Now, I've rewritten this equation by dividing the whole equation by G. So, equation 12a and equation 12b, they are almost the same. Only difference is I have divided by G, and if you note carefully, in equation 12a, you have the gravity vector as G, and here I have used G hat, which is the unit vector in the direction of the gravity. But of course, this holds when there is no shaft work. Okay, this is for the case where there is no shaft work. And
Sir,
yeah.
Sir, for zero viscosity case, sir, you didn't consider the case where the fluid is interacting with the channel through which it is flowing. So there can be a source of friction. So with the fluid, with the channel walls while it flows near the boundary. So won't that contribute to any entropy generation?
Now, if it's an ideal fluid, it will slip along the wall. Okay, so the no slip condition will not be valid, will no longer be valid, and you will not have any viscous forces. So if we say it's an ideal fluid, then there will be no loss.
Sir, I think that is covered in the head loss term, that interaction.
Because of course there is no fluid which is an ideal fluid. Okay, so in engineering situations, you will always be dealing with viscous fluids. That is why we are accounting for the head loss term. But sometimes the head loss term may be a small fraction of the total energy transfer, in which case you can get a prediction by neglecting it. You neglect it just to simplify the analysis, that's all. Okay. In reality, head loss will always be there.
And like in porous material or something, it will be very much large.
Now, if there is porous material, then mass might go through the material. So this equation will no longer be valid. So here you have, assuming that you have a control volume with solid impermeable boundaries, and you have one inlet and one outlet. Okay, you have made a lot of assumptions. You are applying global balance of total energy, but that's not the only thing. You have made a number of assumptions. You assume that the flow quantities do not vary across the inlet, and the flow quantities do not vary across the outlet, but the flow quantities at the inlet and outlet are not the same. Okay, so if you look at viscous flow, then you can apply it only along a streamline or a stream tube. Okay, but if you assume the flow quantities to be one-dimensional, then you can also apply this to the control volume with one inlet, one outlet. So if you have a porous wall, then there will be mass transfer across the walls, solid walls also. So this head loss represents irreversible work done against viscous forces between adjacent layers of fluid. So that's why I called it internal fluid friction. Okay, and this leads to a decrease in the available energy or the useful mechanical energy. In your course on thermodynamics, you must have studied about available energy. Okay, and of course, energy cannot be destroyed, so this decrease must show as an increase somewhere else. So the decrease in the available energy is reflected as an increase in the internal energy of the fluid, and it also leads to a generation of entropy. So if there is no generation of entropy, it will be reversible work, but this is irreversible work. Now, when there is an increase in the internal energy, the temperature of the fluid will also rise. So when adjacent layers of fluid glide against each other, the work done against the friction leads to an increase in internal energy and a heating of the fluid. The temperature of the fluid will rise, and that will lead to inevitable heat transfer from the fluid to the surroundings. Or if you're considering just the fluid inside a stream filament, then the heat will be transferred to the surrounding fluid. So the term in the steady flow energy equation, which represents head loss, includes the increase in internal energy as well as unavoidable heat transfer to the surroundings. So if I go back and see what we have covered this for, the equation number 12a and 12b, you can think of it this way. It's just the definition of the head loss. Okay, but I have explained to you where that loss of available energy goes by looking at the first law of thermodynamics. Now let us consider a case where you also have sharp work as well as head loss. Now what I'll do is I'll close this document, I'll stop sharing and open another document. All right, now let us go back to the first law of thermodynamics. We wrote it in this form where we have the work term on the left hand side of the equation and the other terms on all the other terms on the other side of the equation. So you can see what are the terms which contribute to the work. The first term is due to change in pressure. Second term is due to change in kinetic energy. Third term is due to change in potential energy. And the last term here I have grouped together the change in internal energy as well as the heat transfer. Now consider a case where you have work transfer, okay, but you are not intentionally adding any heat to the system or taking any heat out. Okay, in that case, the last group of term you can identify as the head loss term. Okay, but I'm also keeping the work term now, which we did not have when we looked at just the flow in the duct. Okay. So, as I have shown before, the last term in equation 3 is the head loss multiplied by G. Okay. And if you look at the head loss term, you have E2 minus E1 minus Q dot in by M dot. Whereas in the equation 3, you have E1 minus E2 plus Q dot by M dot. So there will be a negative sign also over here. Okay. So if you account for the negative sign, I can write that equation in this form. W dot sharp divided by
Sir.
equal to a term which involves the decrease in the pressure plus a term which reflects the decrease in the kinetic energy plus a term which reflects the change in potential energy minus a term which reflects the head loss. So this is an equation where in this equation you are not dealing with the abstract quantity which is your internal energy change. And
Excuse me, sir, I have a doubt.
yeah,
Sir, could we go to the previous equation, like the first law?
which one? This equation?
No, sir, above, like the first law equation.
This
This
equation
equation.
3.
Yes, sir, yes, sir, yes, sir.
Yeah.
So, sir, according to the definition of head, as we defined previously, can't we consider the first three terms on the right hand side to be head loss?
First three terms reflect the decrease in the mechanical energy.
Sir, so we defined it as head, right? So, like, if we go by that definition, we could interpret these three terms as collectively as head loss. So, head loss will go into shaft work and internal energy increase. We could interpret it that way.
No, head loss we showed is 1 upon G2 minus E1 minus Q dot by N.
That is when there's no shaft work, isn't it?
When there is
But
no
here
shaft.
there is shaft work.
Here there is shaft work as well as head loss. But you're not deliberately adding any heat or taking any heat out. The heat transfer is just unavoidable heat transfer due to temperature difference.
So basically the head loss due to shaft work is not said as head loss. Rather it is kind of like converting head into work.
So this is just the head loss between sections 1 and 2, a global quantity. When the fluid particle moves from section 1 to section 2, the inlet to the outlet, its specific internal energy is changing. Okay, that is all.
Yes, sir.
So what we are trying to say is that by doing work, you can alter the mechanical energy, or by extracting work, you can alter the mechanical energy.
Yes.
Okay.
Yes.
So you are writing the equation in a form where you don't have, as you in a course on basic thermodynamics, you would have been dealing with changes of internal energy or enthalpy, whatever it is. We are not interested in changes of internal energy or enthalpy as far as hydraulic turbines are concerned. We are just interested in the change in the mechanical energy and the head loss. Okay. So what we are saying is that the shaft work which you're getting because the pressure is decreasing, the kinetic energy is decreasing, and the potential energy is decreasing. And had the head loss been 0, you would have got the maximum work. But if there's a head loss, then whatever work you would have got for an ideal fluid, the actual work will be less by this amount, which is the loss. So when you're trying to convert the energy of the fluid to work, okay, you're not be able to convert everything. You'll be converting some energy inevitably to internal energy also, and there may be some heat transfer, so the work will be less. Okay, that's one viewpoint. The other viewpoint is, let me write this equation 6 in this way. Left hand side is the same. This first three terms I can write as G times H1 minus H2. Okay. So if I divide the whole equation by G, we have W dot shaft by M dot G is H1 minus H2 minus head loss. Okay. Or W dot shaft is, instead of M dot, I've written rho times the volume flow rate, Q subscript flow, into G into the decrease in the head minus the loss of head due to viscous effects. All right. Now, if you look at it in another way, I can write this equation with H1 on one side and H2 on the other side. Okay. So, if you look at what is the head at the downstream section, it is the head at the upstream section minus the head loss plus the work done. Okay. So, if you are, as in the case of a pump, if you do work on the fluid using an electric motor, the head will actually increase. And in the case of a turbine, you will extract work from the fluid, so head will decrease. So the change in head from 1 to 2 is due to two effects. One is the inevitable viscous loss. Okay, whose sign is fixed. But in addition, there is also a work term. So by doing work on the fluid or extracting work from the fluid, you can change the head of the fluid. This is what the global form of the energy balance is saying. Is that clear now? So this equation is sometimes called the extended Bernoulli equation. It is actually a disguised form of the steady flow energy equation. Okay, but in a thermodynamics course, when you applied the steady flow energy equation to solve problems, you're looking at steam tables maybe and finding out what is the enthalpy at the inlet, what is the enthalpy at the outlet. Okay, so here we are not doing that. hydraulic engineers are not interested in the enthalpy or specific internal energy. Okay, so we are relating the work done to the change in the pressure, change in kinetic energy, change in potential energy, and some inimitable viscous loss. Okay. Now, in most cases, the change in potential energy will be negligible. Okay. So you get work by changing the pressure as well as the kinetic energy. Now, in the first class, I talked about impulse turbines. So in the impulse turbines, there is no change in pressure. So the work is just related to the change in the kinetic energy. And the Pelton turbine, which we started discussing, falls into that category. The pressure at the inlet and outlet are the same. But you can have what are called reaction turbines, where you extract energy from the fluid by not only by decreasing its kinetic energy, but also by decreasing its pressure. So you get more work out of it. But the change in potential energy is actually either zero or negligible. And this may be a small fraction. So today what we have done is, we have just identified, reviewed some things which I've already seen before, but I have introduced the notation and some more terms like head and head loss. Okay, and I've talked about the modified Bernoulli equation for duct flows and the extended Bernoulli equation where there is work transfer also, but we are not looking at the change in entropy or enthalpy. Okay, so equation 6 is actually the first law of thermodynamics in a disguised form. Now, some of you have another class at 3. It's my time is already over. It's 2:55. So I'll stop here. But if you have any queries, I can answer that.
Hello, sir.
Yeah.
Sir, does the head loss include the friction factor and the surface roughness?
Okay. When you want to estimate the head loss, you may require the friction factor. Okay. Suppose you want to estimate head loss in a pipe. Okay, then it will be the Darcy friction factor F into L upon D, where L is the length of the pipe and D is the diameter, into V square by 2G, where V is the average velocity. And the friction factor will depend on the Reynolds number and the roughness factor. If it's turbulent flow, and it will depend only on the Reynolds number if it is laminar flow. So if it's a circular pipe, then F will be 64 by RE, which you get by solving the Navier-Stokes equations. But that is in duct flows, laminar duct flows. Okay. So in your second year course, you might have looked at the Moody diagram or the Moody chart, and you might have solved some problems where the flow is turbulent, and you may sometimes require iterations to find the flow rates, etc. But there you did not have the work term. There is a useful work term here, the short work. Okay. Now we are dealing with turbo machines, where there will be some short work. So the left hand side might be either positive or negative. The m dot we'll assume is always positive, but the w dot can be plus or minus. The head loss will always be plus here. Okay. But in the case of a pump, this P2 will be larger than P1. So this quantity will be negative. But in the case of a turbine, either P1 equal to P2 or P2 will be less than P1. So what I'll do is I'll take a look at it and try and remove as many typographical errors as possible, and then I'll upload this somewhere. Okay. I could either send it through ERP mail, or all of you have a Moodle account.
No, sir.
You don't have a Moodle account.
We have activated Moodle. Like for some courses, it's necessary.
Okay, so I have to figure out also how to add your names to the Moodle account.
Yeah, yes, sir.
Sir, or else you can.
Then I can upload it in
MS Teams.
We'll eventually have to do it. But see, this format of teaching is new to all of us. Okay, and typing in even simple things is taking so much of time with the proper font and the subscripts, superscripts. Okay, that I'm not able to find time to figure out how to add your name to Moodle. But eventually, I'll do it. And as you know, I'm taking Professor P.K. Das's classes also this time. Okay.
Oh, so okay. So, sir, you will be taking power plant also.
He'll be talking about power plant engineering. Yes.
Okay.
So for the timing, what I might do is I might just send it to you through ERP mail, and later on I may also upload it in Moodle when I figure out how to do it.
Sir, you can upload it here only in MS Teams itself in the
I can upload
files.
it here also, right?
Yes, in the files tab in the
Okay,
team.
okay. I'll figure out how to do that. Yeah. And after I upload it, you may go through it and you may find some either typing errors or maybe some other errors also, whatever it is. If you find any error, please feel free to get back to me. Okay, I'm typing this in a hurry. There can always be some errors. Okay. Okay, so I'll stop now today.
Yes.
Thank you, sir.
Sir, when will be the next class?